Today we are looking at the paper Render of Thought, rendering textual chain of thought as images for visual latent reasoning.
This one is by Yifan Wang and a team from Tencent BAC and Tsinghua University.
And it really, it fundamentally rethinks how we do reasoning in large language models.
It's a fascinating switch from pure text to, well, vision.
Okay, so for all you engineers listening, here's the 1-minute summary. We all know chain of thought, or Cote prompting, is the gold standard for getting models to reason correctly.
You tell it to think step by step, and it actually works.
But that verbosity is a killer. It just eats up your memory and absolutely destroys inference latency.
Exactly. So people have been trying this idea of implicit code, basically, getting the model to do that thinking in its hidden layers, the latent space, without writing it all out.
But that almost always fails. It's unstable, it's a black box, it's just hard to train.
Right, so enter render of thought, or ROT. They take that reasoning text, and they literally render it as an image.
A picture of the text.
A picture of the text. And they use the frozen vision encoder from a vision language model to act as a kind of semantic anchor.
So they're forcing the LLM to align its internal thoughts with these really dense visual embeddings.
And the results are pretty wild. They're getting 3 to 4 times token compression compared to the old explicit Cote.
And the speed up is huge. I mean, on the GSM hard data set, inference time dropped from about 8.5 seconds down to just 1.84 seconds per sample.
And crucially, it beats the other latent reasoning methods like Coconut and Kohler on both stability and accuracy.
Okay, that's the 60-second version. Let's get into the deep dive.
Let's do it.
I really want to start with the problem itself, because every single ML engineer has felt this pain, the token tax.
Oh, absolutely. It's the classic trade-off. Chain of thought was this amazing breakthrough. Before Cote, models were just kind of pattern matching.
Right, surface level stuff.
Exactly. With Cote, they could actually decompose a problem. But from a systems perspective, it's a complete nightmare.
If you need 500 tokens of thinking just to output a single number, well, your real-time app is dead on arrival.
Forget about it. And it's not just latency, it's the KV cache, it's throughput, it's everything. So naturally, the big push has been to compress that thought process.
And there have been a couple of schools of thought on how to do that, right?
Right. The first one is what you'd call explicit compression. So things like R1 compress or just, summarizing the chain of thought. You keep the text, you just try to make it shorter.
Which, I mean, it works up to a point.
Yes.
But you can only remove so many words before the logic just falls apart.
Precisely. You're still kind of fighting against the sparse nature of language itself. So that led researchers to implicit compression.
This is the telepathy approach.
The telepathy approach, I like that. The idea is so seductive, Why does the model need to say the steps? Can't it just think them?
And we saw this with papers like Coconut and Kodiak. On paper, it sounds perfect.
It does, but in practice, it's just incredibly difficult to train. The biggest problem is supervision. With explicit Cote, you have a loss function on every single word of the reasoning. The model gets constant feedback.
But with the implicit methods, you're just optimizing for the final answer.
That's it.
So it's like the model is wandering around in this high-dimensional dark room, and you only tell it good job if it stumbles on the exit by accident.
That is a perfect analogy. It has no trajectory. The internal states are just these opaque vectors. And without a map, you get vanishing gradients, or worse, representation collapse, where the model just gives up learning anything meaningful.
It becomes this black box that's actually dumber than the base model.
Which is often what happens. And this is where render of thought comes in with this, completely left field solution.
Right. They just say, okay, text is too sparse, raw vectors are too chaotic, let's just use images.
It seems so counterintuitive, doesn't it?
Yeah.
We usually think of image processing as the heavy, expensive part. Why would adding images speed up a text model?
That was my first reaction to, great, another vision transformer to melt the GPU.
Yeah.
But the secret sauce seems to be all about information density.
You've nailed it. Think about how a VT works. It breaks an image into patches, right? Say 14 by 14 pixels.
Sure.
Well, a single one of those patches, if it's an image of text, can hold multiple words or a complex math equation or a structural relationship.
So one visual token carries way more meaning than one text token.
Way more. It's a high bandwidth connection. But there's a second reason they went with vision, and it's even more critical. It's not just density, it's structure. They call it the semantic anchor.
Okay, unpack that. This feels like the core idea that makes ROT work where others failed.
So remember, our model lost in the dark room. Instead of forcing it to invent its own map, ROT just hands it one that already exists.
How?
They use a pre-trained vision language model, in this case Qwen3VL. That model already has a vision encoder that's been trained on, mountains of data to understand the structure of the visual world.
So that pre-trained encoder is the anchor. It defines what a valid thought is supposed to look like.
Exactly. They're forcing the LLM's internal, messy linguistic states to align with this very rigorous, very structured visual embedding space. They're not teaching it a new way to think. They're teaching it to translate its thoughts into a language the vision system already speaks.
That's really clever. You're just leveraging all the compute that's already been spent training these massive VLMs. So what about the architecture? Is this some huge new model?
No, and that's the beautiful part for any engineers listening. It's a plug-and-play setup. You take your standard VLM backbone, like a Qwen3 VL2B or 4B,
Okay.
and you take its vision encoder, and initially you freeze both of them.
So if the LLM is frozen and the vision encoder is frozen, where does the learning happen?
They add one tiny new piece. It's called a visual projection head. It's just a simple 2-layer MLP with SwellGU activation. Sits right on the output of the LLM.
Okay, so walk me through the data flow. Normally an LLM spits out a hidden state that becomes a word.
Right. But in row T, that hidden state goes into this new projection head. And that head's only job is to transform that state into a vector that looks exactly like an embedding from the vision encoder.
So these are the visual latent tokens. The model is kind of hallucinating image data.
That's the perfect way to put it. It's generating the representation of an image of text without ever generating the pixels.
And that's why it's so fast. You skip the whole rendering step during inference.
You stay entirely in the embedding space.
But you can't just bolt this on and go. The paper talks about a really specific two-stage training framework.
Yes, and you absolutely need both stages. You can't skip one. Stage 1 is called visual alignment. This is where you teach that little projection head what a visual thought even is.
How does that work?
So you take your data set of columns and their full text chain of thought answers. You take the reasoning part, the COT, and you literally render it into an image file.
A picture of the paragraph of text.
Right. Then you pass that real image through the frozen vision encoder.
Okay, so that gives you the target, the ground truth embeddings for what that thought should look like.
Precisely. That's your target. Then you feed just the question into the LLM. And you use teacher forcing to train only the projection head to minimize the difference, the mean squared error, between the LLM's internal state and those target embeddings.
You're forcing the LLM's brainwaves to match the vision encoder's eyeballs.
That's a great way to put it. You are. You're just learning that translation. And remember, the big LLM backbone is frozen here. Only that tiny projection head is learning.
Got it. So at the end of stage 1, the model knows how to translate the idea, I need to subtract 5 into a visual vector. But it doesn't know how to solve the problem itself yet.
Not yet. It's just a translator. That's why you need stage 2, latent supervised fine-tuning.
Okay.
So now you freeze the vision encoder and you freeze that newly trained projection head. But you unfreeze the LLM backbone, usually with LoRa, to keep it efficient.
And now the training wheels come off.
Sort of. Now you let the model drive. You give it a question, and it has to generate that sequence of latent visual tokens all by itself, auto-regressively.
And then it spits out a special end token.
Exactly. It generates its visual thought trajectory, then a special embed token, and then it switches back to text to give you the final answer.
I saw something really interesting in the paper about the loss function for stage 2. They stop using the image entirely.
Yes. This is the real aha moment. In stage 2, there is no more visual regression loss. You're not comparing its thoughts to a ground truth image anymore. You are optimizing purely for next token prediction on the final text answer.
I have to push back on that. If you aren't checking if the thoughts look like images, what stops the model from just making up junk vectors? How does it say visual?
Because of that frozen projection head, that head is a bottleneck that was trained in stage 1. It only knows how to output vectors that live in that specific visual space.
I see.
So even though the model is only trying to get the right answer, that frozen head constrains its thinking. It forces the reasoning to stay in the visual lane without needing the explicit supervision anymore.
That is incredibly elegant. It's like you train a runner on a marked track. Once they have the muscle memory, you can remove the lane markers and they'll still run in a circle because it's the only path they know.
It's the exact same principle, and this gives the model the freedom to find even more efficient paths within that visual space.
Okay, let's talk about the rendering part. I assume they were just taking a screenshot of a paragraph, but the paper says that failed completely.
It failed miserably. Their first try was using standard square images, 124 by 124, wrapping the text like you'd see on a web page, and the model performance was terrible.
Why? Why would the shape of the image matter so much to a neural net?
It's all about causality. Text is strictly sequential, left to right. But a square image has two-dimensional spatial relationships. Up, down, left, right.
So if you wrap the text, a word at the end of a sentence might be physically right underneath a word from the beginning of the sentence.
And the vision encoder sees them as neighbors, but the LLM knows they are logically distant. It creates this massive conflict between the spatial understanding and the sequential logic.
It breaks the whole next token idea. So what was the fix?
The single-line rendering strategy. They render the text as one super long, very thin strip, a fixed height of 32 pixels, but a dynamic width.
Like an old stock market ticker tape.
Exactly like a ticker tape. It forces a strict left-to-right processing order that perfectly matches how text is generated. It removes all of that spatial ambiguity.
And what did that one change do to the results?
It was a huge jump. On the GSM-8K benchmark, accuracy went from 32.7% with the square images up to 37.8% with the single-line strip. The geometry of the thought literally changed the quality of the reasoning.
That's wild. Okay, another detail. How does the model know when to stop thinking? In text, it's an end-of-sentence token. What about here?
This is the termination problem. They tried two things. First was dynamic termination, where the model learns to predict that special imgend token.
Seems like the most natural way to do it.
It does, but they found it was pretty unstable. Sometimes the model would stop way too early or just keep generating thoughts forever, so they ended up using static termination.
You just give it a budget.
You give it a budget, you get 32 latent tokens. Or 64. That's it. Use them wisely.
That feels a little restrictive, no? What about harder problems that need more steps?
You'd think so, but it actually made the training significantly more stable. It forces the model to be efficient and compress its reasoning into that fixed capacity. It turns out a predictable thinking time helps it organize its latent space better.
All right, let's get to the numbers. The part everyone's been waiting for. We know the speed up is insane. 8 seconds down to less than 2 is a game changer. But there's always a trade-off with accuracy.
Always. Fast, cheap, good pick too. But Roti does a pretty good job of bending that rule. They tested on all the usual suspects, GSM-8K, SVMP, multi-arith.
Let's start with the compression.
Okay, so explicit VLT, the full text version, takes around 108 text tokens to solve these math problems. Roti does the same job in about 32 latent tokens.
So that's almost a 4 times compression.
It is, and that's where that 4x speedup comes from. Now for accuracy, let's be honest about it.
Give it to us straight.
On Qwen 3VL4B on the GSM-8K dataset, the slow explicit KT gets 79.3% accuracy. ROT gets 55.4%.
Okay, so that is a significant drop. It's not free reasoning.
It is absolutely not free, but you have to compare it to the right things. First, it's way better than no COT, which is just asking for the answer directly. But the real comparison is against the other latent methods.
The other telepathy models.
Right. On that same test, Caller 2 got 47.3%, Coconut got 31.6%, Kodiak was way down at 9.7%. So Roti at 55.4% is just crushing the rest of the latent reasoning field.
So the takeaway is, it's not as smart as writing out a full essay, but it is way smarter than just guessing. And it's the best of all the fast thinking methods by a long shot.
That's a perfect summary. And on the really hard stuff, like the math dataset, it becomes even clearer. With just 64 latent tokens, RT got 33.2% accuracy. The no-caught piece line was only 29.4%.
So those 64 visual tokens are provably doing real reasoning work. They're adding value.
They are adding real value. It's not just noise.
Let's quickly touch on the ablation studies. What happens if you try to cut corners on their training process?
They were ruthless here. They tried removing stage 1, the alignment phase, and accuracy on GSM-8K just plummeted from 37.8% all the way down to 24.8%.
Wow. So if you don't give the model that visual map first.
You get that representation collapse we talked about. The latent space just becomes unstructured soup. The model essentially goes blind.
And what if you skip stage 2, the fine-tuning?
Then the model can translate its thoughts, but it can't connect those thoughts to the final answer. It's like having a brilliant internal monologue but being unable to speak. You need both the map and the driver.
You know, the most provocative part of this paper for me is what it implies for the future of model architectures. We've just spent years assuming that language is the ultimate way to represent thought.
It really does challenge that. Language evolved for communication between humans. It wasn't necessarily designed for high-efficiency computation. This paper really suggests that, maybe language is just too sparse.
A picture's worth 1,000 words. Or in this case, a picture's worth 100 tokens of compute time.
I think that's it. By moving into the visual embedding space, they're accessing a much denser, much richer way to represent complex ideas. Maybe thinking happens in this high bandwidth visual channel, and language is just the I/O layer.
And it kind of solves the black box problem, doesn't it?
Yeah.
If these latent thoughts are aligned with a vision encoder, couldn't you, I don't know, decode them back into an image?
Theoretically, yes, the paper mentions this. You could potentially run those latent tokens through an image decoder and actually see what the model was thinking. It's not perfect, but it's a whole lot more traceable than a random vector in a dark room.
So render of thought. It's faster, it's denser, and it's a clever hack to use a vision encoder as a guide for an LLM's internal monologue.
And it does it all with just a tiny plug-and-play projection head and some smart fine-tuning. For any team out there struggling with COT latency in production, you have to read this paper.
That brings us to the end of this deep dive. If you want to check out the code, it's available in the Tencent BEC GitHub. We'll drop a link in the show notes.
Yeah, definitely check out their single-line rendering script. It's a really elegant little piece of code.
Thanks for listening to AI Paper Podcasts. We'll see you in the next one.
See you then.